We're going to continue on reviewing. We got through, I think, exam one stuff, chapter 10. So let me see here. I think then we went back to chapter 4. Try that one. There we go. So chapter 4 was really about the atom, I believe. And in this chapter, we talked about obviously those experiments that were important for the discovery of the atom. Remember, there was really the CRT sort of tube that Thomson used, the cathode ray tube, to investigate the electron. Thomson, along with Milligan, who did that oil drop experiment. They were able to really, using both of those experiments, one was able to figure out the charge, the mass of an electron. The other one was able to figure out the charge, Milligan. And putting those together, we were able to get the mass of our electron. That was followed up by really the idea, as they talked about, that the atom was neutral. So they knew it did have obviously electrons. So it had to have some type of positive charge to balance that out. And that was sort of Thomson's model, which was the plum pudding model. And remember, that model there was basically a sphere of positive charge with negatively charged electrons embedded inside. They felt that most of the mass of the atom was the electrons in that early model. And again, this was sort of the accepted model of the atom for a bit until really the next major sort of experiment that we talked about, which was Rutherford's gold foil experiment. And Rutherford's gold foil experiment, right, he shot alpha particles at pieces of gold foil. What he expected to happen was, because the alpha particles are positively charged, he expected them to kind of go through with a little bit of deflection here. And he was surprised, right, that pretty much most of them sail through with no problem. And then every so often there would be these alpha particles that would be scattered at these large angles. So what that had to do was they had to kind of revisit the model of the atom and kind of move away from this one and come up with sort of the current model of the atom, which is that the atom is mostly empty space. And again, that is why most of those guys, alpha particles, went through with no deflection. It does contain a dense positive core, right? And that dense positive core is the nucleus. Later found in experiments, right, that is where protons, which are positively charged, and neutrons in 1930 that have no charge were sort of discovered. And that in that empty space is sort of where we have our electrons out in that empty space, moving around pretty randomly as well. And really the other major sort of difference is most of the mass is actually made up of the nucleus. And that is because, as we talked about in those, yes. No, yeah. The charge and mass of an electron. Yeah, because Milligan did the oil drop experiment, and that was the one where he was able to kind of adjust the electrical field, and he was able to figure out the charge of an electron. And that with the mass, the charge to mass, or mass to charge, whichever way you want to look at it, of an electron is what Thomson discovered by just using it. Yeah. Yep. So most of the mass of the atom is the nucleus, and that's because, as we talked about, protons and neutrons, they're both about 1,800 times heavier than any electron. Remember, actually, the neutron is just slightly the heaviest of all three of those, just slightly beating out the proton. But again, they are both roughly 1,800 or so times heavier than any electron. So again, most of the mass of the atom really is made up of the nucleus, which has those protons and neutrons. We also earlier before this talked about Dalton, which clearly the important thing is he went bowling on Thursday. That's the right answer there. Yes.
The neutron was the heaviest than protons.
Yeah, as neutron and protons, they're almost close, but if you take it out like 4 decimal places, the neutron beats it out a little bit. So it's just slightly heavier, but they're very, very close in terms of mass, but it is slightly heavier than neutron, yeah. And like the electron is much, much smaller. All right, so we got that. Then after we kind of talked about the atom, we got into some other parts of it, which was our atomic number, right? Atomic number is the number of protons, right, there are in a nucleus. And remember, the atomic number can be found on the periodic table, right? It is that number that typically is above the symbol there on the periodic table. Remember that the definition of the atomic number is the number of protons, and that's the only definition of it. But if the atom is neutral, then that will also tell you, right, the number of electrons, since that's the only other negative charge thing there. So it will tell you the number of electrons. That's not to be confused with the mass number, and the mass number is the number of protons plus the number of neutrons there are. And you could use both of those things if you take the mass number and you subtract the atomic number from it. That will give you the number of neutrons. So you could use the mass number minus the atomic number. We also talked about isotopes. Isotopes are basically the same element, but has different masses. And as we talked about, out of protons, neutrons, and electrons, it is the proton, which is basically the atomic number. That is the most important thing, as on the periodic table, right? Every element has its own unique atomic number. So if you know the number of protons, you know what element you're dealing with. And that's why isotopes will have the same number of protons, because they are the same element, but they'll have a different number of neutrons, and that's what gives them a different mass. So isotopes basically have a different number of neutrons, and again, that's where the difference in the mass comes from. We talked about how to write symbols for it, and you use the symbol, and top left is the mass number that you put there, and bottom left is the atomic number. So again, if we had Cu 64, and we'll go 29 on that there. And that would be a way that we can write a symbol, including the mass number and the atomic number. And you can figure out everything from this. So this guy here would have obviously 29 protons, which are positively charged. It has no charge present, which means the number of electrons would have to match. And our number of neutrons, again, would be really our top number there, mass number minus atomic number. And again, that's 35, I think, in this particular case. Now, remember, we also talked about that if somebody does have a charge, you do have to adjust. So if we had the same guy, and let's just say it had a +2 charge, which is an ion, it is still going to have protons of 29. But in this case, because it's +2, it actually will only have 27 electrons here, right? And again, the protons can't change, otherwise you change the element. So it's got to be the electrons. The neutrons here would still be the same, 64 minus 29 in this case. Questions on that there? And let me see here. Then I feel like there's one little other thing we talked about there. Maybe. That's what we did. Okay. In addition, this chapter, this is where we talked about the periodic table itself. So we talked about the periodic table. Let me draw my wonderfully rectangled here periodic table. So we do groups, right? So 1, 2, remember we skipped kind of the middle, 3, 4, 5, 6, 7, and 8. Coming through here. So group 1, going down, we use the representative numberings. remember periods go this way, right? So periods on the periodic table, there's 7 of them coming down. 1, 2, 3, 4, 5, 6, 7. And group 1 on the periodic table is the alkali metals. Group 2 is the alkaline earth metals. Group 7 are our halogens. Group 8 are our noble gases. The part in the middle between group 2 and group 3, right, these are our transition metals. We also have the 2 sort of periods or rows there on the bottom. Those technically go up in this area, right? And that's the lanthanide and actinide series, as those are the 2 elements that they follow on the periodic table. So they technically go up here. So obviously you need to know those groups, as we talked about, periods and those special names. In addition, we did talk about ions as well in this chapter. And ions are things that have charges. A scientific word, things that have charges. And as we talked about a number of times throughout the semester, obviously a cation is a positively charged ion. It results from somebody losing electrons. So what happens is obviously they then have more protons than electrons, and they become positively charged. As we talked about, essentially those are typically our metals that do that for some of those reasons we talked about in later chapters. Anions are negatively charged guys, and those are guys that typically will gain electrons, and those are usually our nonmetals that will do that here. And as we saw there with the copper, or even if you want to look at the sodium, sodium with no charge, again, in terms of the number of protons would match its atomic number, which is 11. Number of electrons would also be 11. Sodium, which is group 1, will make a +1 charge. And again, the number of protons here would be 11. Number of electrons would be 10. Again, 11 positives, 10 negatives leaves you that +1 left over for the charge here in this case. If you took something like fluorine, number of protons would be 9. Number of electrons in fluorine would be 9. Again, no charge on either of those. Fluorine with a -1 would have number of protons still 9 because it's fluorine, but now would actually gain an electron and have 10. And again, that is where the -1 left over comes from. As we talked about, since we have the periodic table there on this slide here, we talked about that when things make, for example, ions, and they're making an ionic compound, there are certain things on the periodic table that have sort of consistent charges. And again, +1 there for our group 1, +2 for our group 2, +3 for 3. Usually aluminum is, again, the one that we talk about. Remember, you got, which I guess I could mention here, right? We have that staircase, which is our semi-metals, by the way. I guess it's good it came back to this. So semi-metals here are metalloids. Right to the left of that staircase are metals, right? Upper right of the staircase are nonmetals, right? Now, when we get to group 5, -3 for our nonmetals, -2 for our nonmetals, and -1 in group 7 also for our nonmetals is what we're talking about. Transition metals, as you know, again, have a variable charge, but there are 3 in there that have a fixed charge, and that is your zinc and your cadmium. And those guys will be +2, hang a left over there to silver, and that's going to be +1. So also a reminder, as we talked about, that if it's something off the periodic table by itself, naturally how it comes, and it's not combined with anything else, they do not have charges, right? So things really only get charges, for example, when metals and nonmetals come together. That's when you're going to get the transfer of the electrons, and that's when you're going to get things that have charges. So just anybody from the periodic table really doesn't have a charge unless it's sort of combined with like a non-metal metal situation. Any questions on that there? Yeah.
About like the mass number.
Yeah.
Or we an element, as long as it doesn't have like a 2+ or anything or a -1, we just neutral charge.
Yeah, so if you're doing anything like that, like mass number, atomic number, need to do the protons, electrons, neutrons, you could assume that it's neutral unless it says something like it's an ion or you see the charge there. Then you would know. By the way, a reminder on that as well, which I might have mentioned there. When you do any of those things, the mass number, the atomic number, right? The protons, electrons, and neutrons, those are all positive whole numbers. And that's why the mass number is, again, not the number on the bottom, right? So the mass number is the number of protons and neutrons, should be a whole number. Remember that on the periodic table, the number on the bottom is the atomic mass and not the mass number. So they are different things. So you don't want to use that as the mass number. I think in addition, when we were talking about ions, we also talked about electrolytes here. I feel like we did. And remember, electrolytes are things that when they go into solution, they produce ions. And because they're able to produce ions, they will conduct electricity. So we have strong electrolytes, which 100% break apart into ions. So if you have something like sodium chloride in solution, it is going to 100% break apart into sodium ions and chloride ions. So 100%, you would have ions in there. You would have none of these guys still together. And that's why it's considered a strong electrolyte. It's basically just going to, as we've talked about, load up your solution with ions, and that's going to allow it to conduct electricity really, really well. I think we use like a light bulb example. The light bulb would really be a bright light bulb, right? We also have weak electrolytes, and they actually mainly stay together. But break apart a little bit. So, as we've talked about in later chapters as well, a lot of weak acids and weak bases are weak electrolytes, and that's where we find a lot of those guys. And they will break apart into H plus and F minus. And here we have our reversible reaction that's going to happen, our equilibrium reaction, really, as we now know from chapter 17. That is where how we know this is sort of reversible. Again, that has a forward direction, right, as we talked about also in chapter 17, going from reactants to products, and a reverse direction going from products back to reactants. And again, this will reach chemical equilibrium, like we talked about in chapter 17. But in this aspect of it, in terms of electrolytes, it will create a few of these ions in solution, but it will mainly stay together. So as we talked about, if you had a beaker of this, you mainly would still have the HF units in there together. You would have a little bit of the ions kind of floating around. And because it still has a little bit of those ions floating around in the solution, it's still able to conduct electricity, but not as anywhere near what a strong electrolyte can do. So it can still conduct electricity. But not as good as a strong electrolyte. So in terms of the light bulb example, the light bulb would be dim. It would turn on, but it wouldn't maybe be very, very bright, almost look like it's dying, but it still be enough to conduct some electricity. The last thing, yeah.
That might you should have both a forward and a reverse reaction because they don't mainly stay together.
It's absolutely right. It's really a reversible reaction, which is really what we talked about in chapter 17. It's really an equilibrium reaction. So this guy will actually reach chemical equilibrium, like we talked about, and basically the HF and these guys' concentrations, they'll lock into place. And what happens is when they lock into place, you have just a little bit of the ions there, and you have mainly, so it really has a small value for the equilibrium constant, like we talked about. And because it has a small value for the equilibrium constant, it mainly stays over there on the reactant side. but a little bit of it will break apart. And that's different than a strong electrolyte. You could think of it as like a one-way street. Nobody's coming back the other way. Everybody's just dumping out into the product side. There's none of those products recombining and coming back the other way. This is really a kind of two-way street. People are kind of going in both directions. In this case, it's mainly going to the right, but some guys are working their way back up the other way. It's kind of like the big giant crowd walking down and trying to exit. There's one or a few people that want to go against them, right? And so you got a few people kind of walking against the giant crowd going out. And so that's what's happening. There's kind of that two direction and those type of things. Yeah. Other questions? A non-electrolyte will be something that is something that will dissolve, but the deal here is you get no ions. So I think sugar is an example of that we use. You can take sugar, it will dissolve in water, and you will get aqueous sugar, but because sugar is basically covalently bonded, it's all carbons, hydrogens, and oxygens, you don't create any ions. And because you don't create any ions, it does not conduct electricity. Yes, sir.
Would that be true for both covalent bonds that are
Yeah.
electrolyte?
Yeah, I would say most covalent bonds, that is true. The one exception is, in a sense, because something like an acid is technically still kind of covalently bonded, but what happens with something like an acid or a base is it's able to release that H plus. So by being able to release that H plus, it then becomes more like ionic in solution and stuff like that. But it is true pretty much mostly with covalent bonds, because they are covalently bonded, you don't really have any ions. So even though it may dissolve, if it does dissolve, it's just going to dissolve really as a whole thing and stuff like that, and won't conduct any electricity. Other questions on that? So that should be, if I'm referencing here, chapter 4. Then we went off to something here. Yeah, we went to chapter 11 next. So chapter 11, we started talking about, dare I say, waves. Right? So in this chapter, this is about electrons, really, electron configuration and all that kind of stuff we talked about. But we started out talking about waves, and remember there's some important parts to a wave. There's the wavelength, which is lambda, right? And that is the difference between two sort of peaks or troughs. We also have the frequency. Remember the frequency, and by the way, the wavelength here is in meters. Remember, we also see nanometers as a common wavelength and centimeters as well. But meters and nanometers, and remember nano, which is kind of an important one there, 10 to the minus 9 is a conversion that we use a lot here. Frequency is how many times a wave passes a point in a second. It has units of reciprocal seconds. And remember that a reciprocal second is also a hertz. So it is a 1-to-1 relationship between those two things. So sometimes frequency is given to you in hertz, and sometimes like megahertz, like, right, 10 to the 6. So again, those type of things. We saw a relationship that relates this, which is C is equal to the wavelength times the frequency. C is the speed of light, which is, I think they want you to use the 2 point, trying to remember what number they want you to use, 2.99 number, I think. 997 times 10 to the 8 meters per second. A lot of people just use 3 times 10 to the 8 meters per second, but that's not the number they want you here. I think that is, I might have lost a 9 there, but somewhere in that ballpark is what it should be. And then, so the units of speed of light here, meters per second, units of wavelength, meters when you're using this equation, and reciprocal seconds here are the units that you need. So everything works out right. We could use this equation since C is a constant. If you know the frequency, you can figure out the wavelength. So the frequency would equal the speed of light divided by the wavelength. If you know the frequency, you can figure out the wavelength by taking also C divided by the frequency. So there's a few different ways we rearrange this equation. Remember the idea here, what we're kind of talking about is electrons transitioning, right, from a lower energy level to a higher energy level. And as they maybe transition back, conservation of energy means that the atom will have to give off that energy in the form of a wave, right? And that's sometimes referred to as a photon of light. And that wave will have a specific wavelength or energy associated with it, or frequency associated with it. You can calculate the energy. The energy is equal to h times the frequency. H is Planck's constant, and that is the 6.63 times 10 to the minus 34 joules times seconds here. Now, this, if you know the frequency, you can figure out the energy of that photon of light. Because the frequency equals this, you will sometimes see this as written hc over the wavelength equals the energy. And this would allow you to calculate the energy if you know the wavelength. So you use this equation if you want to calculate the energy, if you know the frequency, or if you know the wavelength, you can use it as well. Now, depending on the energy that comes off as these electrons transition, a reminder that it is an endothermic process. The atom has to gain energy as the electrons go from a lower energy level to a higher energy level, like when you do your flame test, right? Yeah, put your sample in your flame, that adds a lot of energy. And as the electrons go from a higher energy to a lower energy, it's an exothermic process for the atom. It has to release that energy to allow the electrons to come down. Now, as that happens and as energy is being released, it will have a certain wavelength, and it could fall somewhere on what we talked about, which was the electromagnetic spectrum. Right, so we had things like radio waves, right? We had things like uh, microwaves. We had things like infrared. We had things like the visible part of the spectrum, right? That's where we see color. We had X-rays, UV, and some gamma rays. Gamma rays. There you go. And remember, the visible part of the spectrum is where we do see colors. That's where we see our ROI, right? GBIV here. Red, orange, yellow, green, blue, indigo, violet. And if that wave comes off in the visible part of the spectrum, we will see color. Again, like when you did the flame test, what you're seeing, right, is all the electrons being excited and emitting those energy lights that fall at that frequency. Obviously, if it falls outside of that area, you will see maybe nothing, but you might experience something else, like you could experience heat if it's in the infrared and so forth. There is a relationship, right, to waves and energy. So if you have a long wavelength, you usually have a low frequency, and that's usually low in energy. Now, if you have a smaller wavelength, you usually have a higher frequency and a higher energy. So remember, in terms of the electromagnetic spectrum, on the radio side here, that is a long wavelength, low energy. On the gamma ray side, that is a short wavelength, high energy, right? Again, as we talked about why they step out of the room, right? When they give you x-rays, because it's really high in energy. Also why they give you a lead vest. That also goes for colors. And in terms of colors, red is actually the lower in energy, and the purple violet side is actually higher in energy, smaller wavelength. Remember that the colors are usually given in nanometers. So a lot of times in the visible part of the spectrum, like 400 nanometers or so to 7, that's usually given in nanometers. The rest of it, usually a lot of times, is given in meters. Any questions on that there? All right, so we talked about that. We then talked about, again, this idea that as electrons do transition from one energy level to the next, there's a quanta of energy that is used to do that. And that means that they will really only gain or lose enough energy to fully make those transitions. And that is related to that equation that we saw. So as we were talking about, if you had an electron, say here, it will gain enough energy to completely get to that energy level. It will not stop in between. And the idea of quantized energy, if you remember, we talked about sort of stairs. So like, again, when you're walking stairs, you're either on this step, this step, this step, or that step. You're nowhere, bless you, in between. And that's different than a continuous spectrum, which happens with like the sun, and it gives off energy at all parts. And like a continuous spectrum is like you're just walking up and you can stop anywhere on a ramp or something like that, right? You can lay up anywhere on that sort of ramp. And this gives two different types of spectrums. This gives a continuous spectrum, which you basically see everything come out all at once because it can basically stop anywhere. Here with a quantized sort of system, we get those line spectrums, right? And those line spectrums gives us distinct lines at specific wavelengths, and each of those lines correspond to a specific electron transitioning from one energy level to the next. Yeah.
Photons or electrons on that?
It's electrons, yeah. So basically all this has to do, basically this whole chapter had to do with basically electrons and kind of what's happening as they kind of move around in the atom. So yeah, it's definitely all about electrons. And each of these lines in this line spectrum, like for atoms of elements, they give up these typically quantized sort of transitions, and that results in these really specific lines that develop at specific wavelengths that correspond to, as you just mentioned, the electrons transitioning from one energy level to the next. Now, one person that tried to explain what happened or why we see these lines, for example, with hydrogen was Bohr, right? And Bohr had his hydrogen model there. And his was that planetary model, if you remember. You had the nucleus, and then you had these orbits, right? And this was n is equal to 1, n is equal to 2. Remember that n is equal to 1 is the ground state. It is the lowest in energy level, basically. So n is really the principal quantum number. And it's a fancy way of basically just saying energy level, basically. So that's basically your energy level. Anything that's above n equals 1, n equals 2, 3, 4, 5, 6, 7, those are excited states, our higher energy level. And that's obviously higher in energy. And what he's described was an electron, again, transitioning from one energy level to the next. And, you know, it will correspond to these different lines that we see. Obviously, if something came off at a much shorter wavelength, that is a higher in energy transition, which means the electron traveled a lot more energy levels, right? And if something came off, for example, a line in a lower or a longer wavelength, that's a much lower in energy, which means the electron maybe only transition one energy level or two, not as much energy transitions in terms of the levels. So based on sort of the energy associated with those guys, you can make a guess as to sort of where it came out. As we also talked about, this idea of orbits and stuff like that worked really well for hydrogen, but as you got past hydrogen with more electrons, it didn't hold up. And we really sort of moved away from Bohr's sort of idea of the atom and this more quantum mechanical idea, things like Schrodinger's equations, Heisenberg's uncertainty principle, and really all those things that we talked about led to this idea of, unlike in the Bohr model where we think an electron's moving in these pretty little orbits and we know for exact where it's at or where it will be, we move away from this idea to this idea that electrons are actually moving fairly randomly around the nucleus. And at no given point in time will you know exactly where an electron is and how it's moving. And really that's what Heisenberg's uncertainty principle was the idea that the more you know about how, for example, an electron is moving, the less you know about where its position actually is. And the more you know about where the position of the electron is, the less you know about sort of its velocity and how it's moving. So with this, we moved away from orbits to this idea of orbitals, right? And orbitals are these really theoretical descriptions, mathematical descriptions, really, of where you find an electron in an atom. And we talked about s orbitals. And when we talk about s orbitals, there is only one type of s orbital, and it begins on the first energy level, on n equals 1. That's where we first start to see s orbitals. Remember that any individual orbital can hold a maximum of 2 electrons. So 2 electrons is all it could hold. So for example, on that first energy level, we have a 1s orbital that basically could hold 2 electrons maximum, and it's going to max out. There are p orbitals, and there's actually 3 types of p orbitals. There are the px, py, and pz orbital, and those don't begin until the second energy level. And that means because there's 3 different types, say this is our 2p orbitals, they could hold 6 electrons. What I'm kind of drawing is also what we also talked about, which is like orbital diagram, right? So orbital diagrams is where you kind of use arrows and boxes to represent electrons. By the way, they do go into this subshell one at a time, right? And then come back and fill up, basically. Bless you. So it could hold a maximum of 6 electrons. Then there are d orbitals, and there are 5 different types of d orbitals. That begins on the third energy level. So 1, 2, 3, 4, 5. And this can then hold a maximum of 10 electrons if you fill them all up. And each of these lines would represent a different d orbital. And lastly, f orbitals, there are 7 different types of f orbitals. That begins on the 4th energy levels where they first start to appear. And again, if we filled up all these guys, I'll do it correctly here for the rest of it. We could put in there 14 electrons, basically. That'd be like our 4D. Remember that when we do have, for example, more than one orbital on an energy level like these guys, all these guys here, these are sometimes referred to as a subshell, right? And that is a subshell. So all these guys together is the P subshell, our sub level. This would all be the D subshell. This would all be the F subshell, right? We don't usually use the word subshell with S since there's only one orbital. Also remember that when we talk about like a shell or a level, we're talking about everybody on that energy level, right? So when we talk about the n equals 2 level, our shell, that would be everybody that's on there. That means you could hold, for example, a maximum of 2, 3, 4, 5, 6, 7, and 8 electrons. You could also calculate if you want to know how many electrons on the shell by doing 2 times n squared. So for example, the one we just did, that's the second energy level. N would equal 2. 2 squared is 4. 4 times 2 is 8 electrons maximum if you filled it all up. If you did the third energy level, 2 times 3 squared. 3 squared is 9. 9 times 2 is 18 electrons if you filled up that entire shell, which would consist of everybody that is there. Any questions on that there? That led us to, I believe, electron configuration. That would make sense, I think. So we talked about electron configuration. We talked about sort of this idea that there is a specific order that occurs and how electrons are put into the atom. You can recreate that sort of chart that you need to write electron configuration, as we talked about, by just remembering basically those four things we just talked about. On the first energy level, there's where S's begin. On the second energy level, kind of go to the diagonal there, P's begin. On the third energy level, that's where D's begin. And on the fourth energy level, that is where F's begin. At this point, you essentially could just fill in the numbers underneath. So you got 2s, 3s, 4s, 5s, 6s, 7s, and then 3p, 4p, 5p, 6p, 7p, 3d, 4d, 5d, 6d, and 5f. And this is the correct order, right? We then arrow it like this. And the main difference where people always sort of mess up is right here. Remember, it does go from 3p to the 4s and then back to the 3D, right? So this will give you the correct order. So again, if you know how to create that like I just did a second ago, and you remember again that S has a maximum of 2 electrons, P is a maximum of 6 electrons, D subshell maximum of 10, and F subshell a maximum of 14. You should be able to write any electron configuration you want. You could write electron configuration by, for example, we'll do iron. Why not? Iron is what we got there, 20. Okay, that's 26, I think, right? That's 26. I hope. Close. 26. 26 is good. I know the thing's like 9 feet big. I should be able to see it, but it's good. 26 looks good. So again, we always start up here, and we would go 1s2, 2s2, 2p6. 3s2. So again, we come this way. We're going to zig back this way, zigzag this way. Coming back now to 3p6. We go here to 4s2 next. Now we zig back, and now we're at 3d. 1, 2, 3, 4, 5, 6, I think there. And that would get us our electron configuration. We also talked about, by the way, again, no commas, no dashes, superscript right on top there. The number on top is technically the number of electrons in the orbital or subshell. The first number is the N number, the principal quantum number, the energy level, and obviously the letter is what orbital or subshell it's in, right, when you look at it. There's also a shorthand, right, when you're writing electron configuration. And if we look at this guy up to this point right there, that is 18 electrons. And if we look on the periodic table, number 18 again is argon. And we could shorthand this as argon, and that's basically saying that is the electron configuration for this guy, 4s2, 3d6 in this case, right? It is always a noble gas that goes in the bracket. So this always has to be a noble gas from group 8 that comes before whatever element you're writing the electron configuration for. Speaking of that, we also talked about, as I mentioned earlier, sort of the orbital diagram, which if you were going to do it here, you would draw it out. Again, a box or a line for each of the ones here. And I'm just going to kind of go to sodium here, so I don't have to go so far there. So we'll go this way. So if we're going to do it for sodium, which is 11, again, up, down, up, down. Remember, Hund's rule means that we go one at a time and then we fill it so they don't have the same 4 quantum numbers. That is Pauli's exclusion rule, which means they cannot have the same 4 quantum numbers. And that's why we go opposite spins, one up, one down in the same orbital. And here would be our orbital diagram. Actually, I went too far. I think on that one extra line is not good. I went to magnesium. Let's get rid of that there. That should be 11 there, 2, 4, 6, 8, 10, 11 in this case. Any questions on that there? Now, I feel like that was it. Let's see here. The last thing we did talk about, I felt like just one last thing. Last thing we talked about here in this was periodic trends, right? Bless you. So for our periodic trends, we'll just draw a giant box periodic table. These trends basically account for a lot of the factors that we see. So one thing that we talked about was Z effective, or effective nuclear charge. That is the energy, or the positive charge that outer electrons feel as a result of shielding. So if you remember something like lithium that has 3 electrons and a +3 charge, they have 2 core electrons, which are the lower energy level electrons closer to the nucleus, not involved in bonding. They have 1 valence electron, right, which is the outermost electron, the highest in energy, the one involved in bonding. These 2 lower guys shield the outer electron from the full +3 charge. So what that guy feels as you calculate it is a +3 charge from the protons minus those 2 electrons that shields it. So that outer electron only feels like a +1 charge. And that attraction is much weaker than those core electrons. And that's why that valence electron can be removed easier, because it's not being held as tightly because of that active shielding. In terms of the periodic table, Z effective actually increases as you go up and right on the periodic table, decreases as you go down. We also talked about ionization energy. That is the energy needed to remove an electron in the gas phase, bless you. And on the periodic table, as we go up and to the right, ionization energy increases and decreases as you go down. Remember that electrons actually come off one at a time, and it gets harder and harder to remove electrons after you take one off, because as you remove an electron, everybody gets smaller, right? And that means those outer electrons are now closer to the nucleus and held tighter, so it's harder to remove. It takes more energy to do so. At some point, when you get to the core electrons, it's so small and those electrons are so close, it's not energy efficient to try to remove those. And that's why we don't lose core electrons, right? That's why we only lose valence electrons. And that's why something like magnesium, which has 2 valence electrons, will make a +2 charge and never really a +3 charge. Yes, sir.
Energy,
Yeah.
that's solely just gas then? So with the gas phase?
Yeah, so that's really how electrons are removed, although we don't talk about it a lot. But what happens, for example, even when you like dissolve like a solid sodium chloride in a solution to make ions, there's a moment there where they actually go into the gas phase, and it's actually at that point where they actually gain and lose electrons, and then they drop, for example, into the aqueous phase or liquid phase. So that's the definition. That's why the definition of ionization energy is the amount of energy needed to remove an electron in the gas phase, because there's a slight little thing, and you'll talk about probably when you talk about solutions in the next class, but there's this little like hydration step where they kind of head into the gas phase for a second to allow them to lose and gain electrons, and then they get rehydrated and go and get dissolved. Other questions? There's also, by the way, right, because electrons come off in different stepwise fashion, first ionization energy is the energy to remove the first electron. Second ionization energy is to remove the second electron. Third, fourth, and fifth, or whatever it may be. And again, it gets harder and harder. We also talked about electron affinity. Electron affinity is the energy change when an element gains an electron. So when we talk about ionization energy, because it's losing electrons, we really talk about it in the sense of like cation formation, things that become positively charged. When we talk about electron affinity, that's when things gain electrons. So we talk about that for anions, right, and nonmetals. On the periodic table, electron affinity increases as you go up and to the right and decreases as you go down. And again, if something has an affinity for something, it means it likes to gain electrons. So something with a high electron affinity means that it's pretty good at gaining electrons, basically. Yeah? That's not to be confused with our other friend, which is electronegativity. Electronegativity is the ability of an atom to bring electrons towards itself. And on the periodic table, it increases as you go up and to the right and decreases as you go down, although not drawn correctly here. Fluorine is the most electronegative. Fluorine's actually way up here, but it's the most electronegative element that you could have in this particular case. All of these sort of periodic trends also is why, as we go to the right on the periodic table, size decreases and size increases as you go down and to the left. And that's because of all those things. Even as you go up and to the right, you have a greater effective nuclear charge. So even those outer electrons, even though they're experiencing shielding, because there's more protons as you go up and to the right, those outer electrons are now going to feel a much stronger pull to the nucleus. It's going to make the overall size of the atom smaller as you go up and to the right and larger as you go down to the left. All of these trends that we see here all account for what we know happens, which is we have kind of our staircase coming this way. Up and to the right, we have really small atoms, electrons held really tightly, and things that like to attract electrons. That's where our nonmetals are. And that's really why these guys make anions. They like to accept electrons. This way on the periodic table to the left, we have our metals. And these are larger guys, don't hold on to their electrons all that much. And these are why these guys typically will make cations, which are positively charged. Any questions on that? Yeah. Ionization energy is the energy that's required to actually pull off an electron, to remove an electron from somebody. Electronegativity is the ability of an atom to actually bring electrons to themselves so that they can gain it. So one is like, if I wanted to take an electron out of this bottle, that's how much energy I have to put in there to take an electron out. That would be ionization energy. Electronegativity would be if this guy gets near that one, he's going to kind of suck the electrons near him because it's going to be attracted. He wants to grab the electrons. And that causes, you know, in some cases, those electrons to be sort of transferred. And that's what happens, right, when we take a metal and a non-metal together. Because nonmetals have high electronegativity, when they get near a metal which has low electronegativity and low ionization energy, it doesn't take a lot of convincing for them to be able to pull that electron away. And that's why in an ionic compound, you get a transfer of electrons that occur. That's different than when you get two nonmetals together when we talk about covalent bonding. Because they have similar electronegativities, neither one of them wants to get rid of that electron. They're both really holding on to it, so they can't get that electron to completely transfer. And that's why, for example, in covalent bonding, we have sharing of electrons that occur. Yeah. Other questions? All right, that is chapter 11. That then brought us, dare I say, to chapter 12, which was everybody's favorite chapters, maybe. Chapter 12 was bonding. Yeah, so we talked about different types of bonding, and I just touched upon it there. We have ionic bonding, which is always between a metal and a nonmetal. And remember that in this case, because of the difference in those periodic trends, the metal is going to basically transfer its electrons over to the nonmetal. That's going to create a cation that's positively charged and an anion that is negatively charged. And that is what holds that together. Remember, there is no sharing of electrons here. And it is electrostatic attraction, opposites attract, that holds that together. We can go to the periodic table, and the number of valence electrons, which are the ones involved in bonding, equals the group number, right? So everybody in group 1 has one valence electron, 2, 3, 4, 5, 6, 7, and 8. The one exception is helium, right? Helium actually only has 2 valence electrons because it only has 2 electrons total. So if we were to draw a Lewis dot symbol for sodium. It is group 1. It looks like this, right? And it has our electron configuration of neon 3s1. And we take chlorine, which is group 7, which means it has 7 valence electrons. And chlorine would be neon 3s2, 3p5. What's going to happen because of the difference in those values, we're going to get the electron to actually transfer over to the chlorine here. I'll go underneath. And what that's going to do is it'll now have sodium lose an electron and now become positively charged. The chlorine here will pick up that electron, and because it picked up 1 electron, it now will be negatively charged. And now we made an ionic compound here using Lewis dot symbols. Remember that what happens with the electron configuration, sodium lost this electron here, that's its valence electron. It now has the same electron configuration as neon. The chlorine gained that electron right there into that orbital, and that now gives it basically the same electron configuration as argon. And that is the whole purpose of bonding, both ionic bonding and covalent bonding, is everybody wants to achieve the same electron configuration as a noble gas. They are isoelectronic, which means they have the same electron configuration as noble gases. And that's because noble gases are really stable. So the goal here is to covalent bonding, ionic bonding, is for everybody to achieve noble gas configuration. Any questions on that there? Now, we talked about covalent bonding. And covalent bonding is always between 2 nonmetals. And with 2 nonmetals, we actually have sharing of electrons, right? And the sharing could be equal sharing, and equal sharing of those electrons is what is known as a nonpolar covalent bond. Unequal sharing of those electrons is what is known as a polar bond. And remember that you could figure this out by using the difference in electronegativity values. So for example, there's that scale of electronegativity values that go from 0 to 4. So if we did something like hydrogen, which is 2.1, I think, and carbon, which is 2.5, and we do the difference there, just take the larger number minus the smaller number here, gives you 0.4. That is considered a nonpolar bond. The limit is 0 to 0.4 is considered nonpolar or equal sharing of electrons. About 0.5 to below 2 is considered a polar bond, and above 2 is typically an ionic bond. Remember, you don't really need electronegativity values for ionic because it should always be a metal and a nonmetal, and if it's not, then it's probably some type of polar or nonpolar bond. We can show bonding in covalent molecules by drawing Lewis structures. So if we had something like CO3 2 minus, remember that when we draw Lewis structures, there's certain steps that we want to follow, which is total number of valence electrons. So carbon is group 4, oxygen is group 6, so there's 6 and there's 3 of them. And remember that when we do have something that has a charge, this is a negative charge, which means it gained electrons. You do have to add the electrons in. So that is going to give me here carbon. I definitely went wrong. I got 4. We got the 18, 20, 24 there. When we draw a Lewis structure, the least electronegative atom should be in the center. Hydrogen and fluorine should never be in the center. Hydrogen should never be in the center because it should only have 2 electrons. Everybody else should have 8, which is the octet rule that we talked about, right? So we're going to single bond to everybody. Remember, a single bond represents 2 electrons, and these are bonding electrons, right? So that's 2, 4, 6 electrons. If we subtract that off, we still have 18 more to go. They go on the outside as pairs of electrons until each of the outside members have 8 electrons, R2 if it's obviously hydrogen. If at this point you still had electrons to put on there, they would go onto the center atom as dots as well. In this case, we don't. We've now used up all 24 electrons. You do want to make sure everybody has met the octet rule, and in this case, carbon has not. And when somebody does not meet the octet rule, that's when we actually want to do double bonds and try to fix it. And then if double bonds don't fix it, we want a triple bond. Remember that we do not want to just double bond right out of the box. But what we want to do here when we make a double bond, so we don't end up with too many electrons, is we're actually going to bring a pair of electrons in to do so. And that is going to get us our proper Lewis structure here. It looks something like this. Now everybody has 8 electrons and still a total of 24 electrons. And you can draw it with a little bracket and a charge because it's an ion. This also can make up something else that we talked about, which is a resonance structure. And that's because we actually could have double bonded to the left here and drew an equivalent structure. And we also could have double bonded to the right here and drew an equivalent structure. And any one of them is an appropriate structure for carbonate here. But these are all what are referred to as resonance structures with each other. This is because those double bond electrons are moving around. They're delocalized. So at any given point in time, they could be at one spot versus the other. With this, we talked about Vesper and a molecular geometry and electron geometry, valence shell electron repulsion model, electron pair repulsion model. And remember that when you do this, if you only have 2 things, a diatomic molecule, the geometry is always linear, right? So it's always linear. It doesn't matter if it's single bonded, double bonded, it's only linear. When you have 3 or more atoms, you have to look at the number of electron pairs on the central atom. It's always the important thing. The number of bonds. That will give you the electron pair geometry, which is one name we talked about. That will also give you a molecular geometry, which is also sometimes referred to as the shape. And that will get you a bond angle, right? So if you have 2 electron pairs and 2 bonds, the electron pair geometry is linear. And linear, bond angle is 180 degrees. That would look something like this, basically. No dots or anything on the central atom. If you have 3 electron pairs and 3 bonds, that is trigonal planar and trigonal planar for both names. Also sometimes referred to as triangular. That's 120 degrees. It'll look something like this. If you have 4 electron pairs and 4 bonds, that is tetrahedral and tetrahedral. That has a bond angle of 109.5 degrees. That will look something like this. Again, all these guys will not have any dots on the central atom. And that is why both of these names are the same. So when you draw a Lewis structure and there's no dots on the central atom, both the electron pair geometry and the molecular geometry are the same name. It's only when you get those non-bonding electrons involved that you get a different molecular geometry name. So we talked about, I think, 3 electron pairs and 2 bonds. And that's going to give you trigonal planar for your electron pair geometry and that angular guy. That's going to have a less than 120 degrees. So that's going to look something like this with some dots. If you have 4 electron pairs and 3 bonds, that's going to give you tetrahedral. As you can see, the electron pairs and the electron pair geometry name are tied together. That's going to give you trigonal pyramid. That has a bond angle of less than 109.5. So that will look something like this. And lastly, if you have 4 electron pairs and 2 bonds, also going to give you tetrahedral. That's going to be bent or V-shaped, that's going to be a less than 109.5 bond angle. And we'll try to squeeze it in here. A, B, B. Oh, that's wrong there. Bad squeezing. We'll go to the top here. How's that? A, B, B, dot, 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 something like that. Remember that when we're doing geometry, probably the most important thing is everything counts as one, right? So if you have a double bond, if you have a single bond, or if you have a triple bond, they all count as one electron pair and one bond. So that's the really important thing, right? Yes. The difference really is the number of electron pairs and the bond angle. The bond angle for angular is actually closer to 120. The bond angle for bent or V-shape is less than 109. So some people will use bent for angular as well. And some people will use, as we talked about, bent angular. So for here, we use angular just to kind of distinguish it different than bent or V-shaped. But there is a difference in the bond angle between those two. But I will say some books and some people kind of use bent for both, and they kind of interchange and stuff like that. Other questions on that there? That was pretty much chapter 12 since we're out of time here. But we talked about really, just to finish up chapter 12 super quick, molecular polarity. And the quick way to do molecular polarity, right, is if you have a diatomic molecule, if that bond is polar or nonpolar bond, that will also be the molecular polarity. Because it only has one bond, so if that bond's polar, then that molecule is polar. If it's nonpolar, it is going to be nonpolar. If you have 3 or more atoms, remember you could do the quick way by no dots. Basically, no dots on the central atom, all outside the same atoms or elements. Then it's going to be nonpolar molecule. If you have no dots and they're not the same on the outside, it's going to be most likely a polar molecule. If you have dots on the central atom and everybody's the same, it's going to be a polar molecule. So remember, you could do molecular polarity pretty quickly, dots or no dots. So if there's no dots, everybody's the same, non-polar most likely. If there's no dots, everybody on the outside is different, most likely going to be polar molecule. And if there's dots, most likely going to be a polar molecule.